Hi guys, welcome to part 2 of this series. We will continue the example from part 1 and proceed with the calculations of the unknown reactions FYA, FXA and MA as shown in a diagram below. Then we will draw the bending moment and shear force diagram. I have put the link in for part 1 video in the comment sections below in case you have missed it, so please you can go back and watch it if you wish. Now why is it so important to draw the bending moment and shear force diagram? Well, it simply helps us to assess all the positive and negative values of the transverse shear and bending moment along the entire length of the beam. And number 2, we then can work out the section capacity and hogging and sagging, and thus the reinforcements requirements. So what I mean by hogging is when there's a negative moment, which implies that the top of the beam is in tension and the bottom is in compression. Sagging, on the other hand, is opposite, where there is a positive moment and the top of the beam is in compression and the bottom of the beam is in tension. You can see that here in the little diagram here below. And number 3, well, based on the moment values in respect to hogging and sagging, then we can work out the strength requirements in ductility. So let's get straight into it. From the method of superposition in part 1, we worked out the reaction FYB to be 15 kilonewton. So now we have 3 unknowns, and we also have 3 equations of equilibrium. Therefore, the structure is now statically determinant. So the first most important step is to show the direction of the forces and sign convention. A lot of us forget it, but I think this is the most important thing. So for the external force sign convention, I'm going to assume up is positive, down is negative, right is positive, left is negative, anti-clockwise moment is positive, and clockwise moment is negative. Okay? This is my sign convention. You can choose whichever one you're comfortable with, as long as we are all consistent throughout the whole process of drawing the shear force and bending moment diagram. For internal beam forces, so when we cut the beam, there's also a sign convention for that. I will take compression at the top of the beam, shear force down, and tension outwards to be my positive to the left side, and of course equal and opposite forces to the right side of the cut. Okay, now adopting the 3 available equation of equilibrium in respect to the global axis, okay, y, x and z. So forces in the y-axis is equal to 0. FYA is going upwards, minus 25 times 3.6, and that's negative because the UDL is going down, plus 15 is going up, and that is equal to 0. Therefore, FYA is 75 kilonewton. And if you noticed here, the answer is positive, which just means that the direction that we've assumed is correct, which is going up. Okay? Now, forces in the x-axis, there are no horizontal forces, external horizontal forces at all, so therefore FXA is equal to 0. Okay? And then we have sum of moments around the z-axis, so sum of moments at point A. So if you put your finger at A and consider all the moments around point A. So you first have the fixed end moment, MA, and that's going anti-clockwise, so that's positive, MA, minus 25, the UDL, times 3.6, okay, that's going clockwise, times the lever arm, which is 1.8 meters, that's half of 3.6 meters, okay, plus 15, okay, at FYB, 15 times the lever arm, which is 3.6, and that's going anti-clockwise, and that's why it's positive. Okay, working out MA, you get 108 kilonewton per meter. Again, the answer turned out positive here because It just means that the direction of anti-clockwise that we have initially assumed is correct. Note though that the moment it causes the bottom of the beam to be in compression and the top is in tension. This is more of hogging. So that's why that moment is considered to be a negative moment. Okay, now it's time to draw the bending moment and shear force diagram. This is a fun part. I hope we all get it. It took me a very long time to understand it when I was younger at university days, but once I got it, I actually began to really enjoy it. So here I have drawn up the beam again, the beam model with all the values of the reactions, okay? Before we proceed, there are two most important relationships to always remember. I remember at university my lecturer told me if I forget how to draw the bending moment and shear force diagram for any beam, then engineering is not for me. And the truth is I actually forgot at some point in my life, but I've never forgotten these two relationships. Okay, the first one, the derivative of the shear force diagram, which is dV dx, is the value of the distributed load, which really means that the slope of the shear force diagram is the value of the distributed load. Okay? Then from there we can say that the change in shear force, which is delta V, in respect to the length of the beam, is the area under the distributed load. So delta V is integration of W, the load, times dx. And the second relationship, very similar. Now we have dm dx, which is the derivative of the moment diagram, is the value of the shear force. Again, which means that the slope of the moment diagram is the value of the shear force. Same thing as before. We can say that the change in moment, delta m, is the area under the shear force diagram. So delta m is equal to the integral of v dx. Hopefully we can illustrate this more clearly in the drawing of the shear force and bending moment diagram in the next few slides. Okay, let's begin with the shear force diagram. Now we know that the change in shear is the area under the distributed load. Because we have a uniform distributed load, then we simply calculate the area of a rectangle. That's it, which is 25 kilonewton meter. That's the height of the rectangle, okay, times the length of the beam. I think we're lucky in this case because the uniform distributed load is consistent throughout the entire beam. So the area is equal to 25 times 3.6, and that is 90 kilonewton, which means that the change in shear is 90 kilonewton, okay? So then we start from left to right, okay? We always follow the direction of the reactions. So we always start from left to right and then start the directions of the reactions. At left we have a fixed end moment, MA, which does nothing to the shear force, so we can ignore it. We have a concentrated upward force, which we calculated before, 75 kilonewton, FYA. So at point 0, at the beginning of the beam, we go up at a positive 75 kilonewton. Then, because the distributed loads are pointing downwards, we would then start to move down linearly from 75 kilonewton. Okay? Now, the amount we go down is the change in shear, which is the area under the distributed load. This means we will need to go down 90 kilonewton from 75 kilonewton, which will take us down to negative 15 kilonewton. Okay? So again, at 75 kilonewton, we go all the way down to 0, right, at the beam, and then we keep going all the way down, right, and that becomes negative. Once we pass the bottom of the beam, it becomes negative, then until we get down to negative 15. Okay, and this all makes sense because to keep all internal forces in equilibrium, we are expecting that we would have a reaction at FYB of 15 kilonewton, okay, which we calculated before. So yeah, so this is how you do the shear force diagram, and if you understand this, you'll be able to understand how to draw a shear force diagram for any problem. Now it's time to work out the value of x, okay, to determine the area of the shear force triangle. And why is that important? Because we know that the change in moment is the area under the shear force diagram. So to draw the moment diagram, we need to first work out the area of the shear force diagram. There are two ways to work out the distance x, and you may choose any method you're comfortable with. I will go through both of them. Method one is the easier method. From zero, from that point here, to distance x, the change in shear is negative 75 kilonewton. So why is it negative? Well, because the slope is going downwards. So that's negative, okay? It's going downwards. So since we know that the derivative of the shear force diagram is the distributed load, then we could say the change in shear minus 75 kilonewton is equal to the area under the distributed load up to the distance x. Okay, so now we have negative 75 is equal to minus 25 kilonewton per meter times the distance x. So solving for x, we get 3 meters. Okay, the easier method, not the easier, but the more complicated method is using the similarities of triangles. From the shear force diagram, we can compare the two triangles together by saying 75 kilonewton, the bigger triangle, divided by the smaller one is 15, is equal to x divided by L minus x, and then solving for x, you will also get 3 meters. Okay, so now let us go ahead and draw the bending moment diagram. So we basically do the same thing as before. The change in moment is the area under the shear force diagram, which is the integration of V dx. So first we need to work out the area of the triangle A1. A1 is half times x, which we found 3 meters, so half base height, half times 3 times the height of 75, and that will give us 112.5 kilonewton meter. So this means the total change of moment, delta M, is equal to 112.5 kilonewton meter. Then we follow the same rule again, left to right. We start at the fixed end and check what is happening there. But, now we already have a fixed end moment. Okay, we got MA of 108 kilonewton meter going up. So how do I know that it's going up? This is interesting because Americans, they love to look at the beam from the left side, okay? So if you stand at point A and look to the left, you will see that the anti-clockwise moment, MA, is rotating downwards. So Americans usually go down with negative moments. To be honest, it makes more sense, down, negative, yeah? But Australians and almost the rest of the world, they look at the right side of the support. So if you're standing at point A and you look to the right, then you'll see MA, the anti-clockwise moment is actually heading upwards, okay? So we go up with negative moments. I know this all gets confusing, but this is the simplest way I can describe it. So let's stick to the Aussie way for now. So from left to right, again, we will go up 108 kilonewton per meter, but remember this is a negative moment because it causes, tension. It's a hogging moment which causes tension at the top and compression at the bottom of the beam. Okay, so we go up 108 kilonewton per meter, but we have a change of moment from that area under the shear force diagram of 112.5 kilonewton meter. So we need to go down 112.5 kilonewton meter from 108 kilonewton meter. The slope, if you notice, the slope now changes from the linear line in shear diagram to a polynomial, okay? So we keep going down until we hit the beam at 0, but we still have to keep going, another 4.5 kilonewton meters until we reach the total change of moment of 112.5 kilonewton meter. Okay, so we start at 108, keep going down until the end of the beam. So we finished off the 108, but another 4.5 to maintain the maximum change of moment of 112.5. For all forces to balance up, then the second triangle, A2, must equal the area of the second triangle, must equal the remaining moments of 4.5 kilonewton meter. Okay, so let us check this out. A2 is half times 0.6 times 15, right? And the area of a triangle, half base times height. And guess what? It's 4.5 kilonewton meters. So fantastic. So everything seems to balance great. So now we can continue the positive moment, that curve from 4.5 kilonewton meter to 0 at the end of the beam at point B. Remember, there is no moments at the spring supports, so it just ends at 0. Unless, of course, if we had applied a rotational stiffness or rotational resistance at the beginning of the problem, then we would have probably had some sort of moment. But in this case, we only had compression only. We looked at this beam in one single degree of freedom. It's only allowed to go up and down. So yeah, so we assumed 1 degree of freedom. So we don't have any moments at all at the end. So that's going to be 0. So now our design hogging negative moment is 108 kilonewton meters. So that's what we designed for. The design maximum shear force is 75 kilonewton. The sagging design moment is only 4.5 kilonewton meter, and the corresponding shear force is only 15 kilonewton. The last step, of course, is to check the flexural and shear reinforcement to resist these forces. For hogging, you'll have to have top steel, and for sagging, you'll have to have bottom steel. Then, once the reinforcements are selected, we then can check the minimum steel requirements and ductility requirements. Okay, some engineers make life a little easier by just adding the same reinforcements, top and bottom, for the maximum moment in the system. For the maximum moment and maximum shear in the system. But you have to be careful here, because you don't want to have an over reinforced beam. Otherwise, you will get a non-ductile failure. When positioning the reinforcements, always check the neutral axis depth and ensure that you'll get the tensile steel to yield before the concrete crushes. In other words, you want to make sure that the steel fails before the neutral axis actually reaches up to the compression face of the beam. So that's it, I think. Thank you again for watching, and I hope this video was useful. So if you have any questions, please put it in the comments below, and I'm very happy to answer it. So see you next time.